Here I've drawn a circle. From the center of the circle to the edge of the circle, we've got a radius. And the distance around the circle is the circumference. Now, if I double the radius, then what we have is the diameter of the circle. Now, if I take a ratio of circumference divided by diameter, I'm going to get a number always, and that number is pi, which is about 3.14. Now, we call this pi, 3.14, an irrational number. It's only approximately equal to 3.14. It is a non-repeating, non-terminating decimal. That's what classifies it as irrational. So we have had experience with irrational numbers before. Now I'm going to introduce another irrational number to you called e. Let's consider the function y equals parentheses 1 plus 1 over x, all raised to the x power. Now, I've made an xy chart here, and I am choosing the x values. It's me who chooses the x values. Notice what x values I've chosen. Positive x values that are increasing by a factor of 10. Looks almost like a geometric series or sequence. 10, then I multiply by 10, then I multiply by 10 again. In other words, these numbers are getting bigger and bigger and bigger and bigger. Look what happens when I put a 10 in. If I put a 10 in for x there and I raise it to the 10th power. Now, remember, when we raise the 10th power, it's going to get bigger and bigger and bigger. If I do that, then I'm getting 2.59, just about. As I put a 100 and a 100 in, I get 2.7. If I go all the way to 1 million, I get 1 million here and 1 million here. Now, I'm raising something greater than 1 to the 1 millionth power, and I'm getting 2.71. It's really 2.71828. And that is our approximation of Euler's number. And because it's Euler's number, and Euler starts with an E, we call this number E. So that's another irrational number for you to know. Here are our big takeaways. There's there's probably more, but there's at least two irrational numbers, non-repeating, non-terminating decimals that you should be familiar with. Pi is about 3.14, it's not exactly equal to that. And E, Euler's number, is about equal to 2.7. Remember that this is 1 plus 1 over x to the x. Now, we're going to figure out what happens as x gets bigger and bigger and bigger. And I don't want to say as x gets bigger and bigger and bigger. The way I write that is we're going to take the limit of this as x goes to infinity. So that means start small and go bigger and bigger and bigger with x. Of course, we're going to learn more about limits in chapter 12. What if we wanted to graph f of x equals e to the x? One thing to know for certain here is that the variable is the exponent and our base is greater than 1. This is essentially akin to doing something like this, taking a base of 2.7. Now, I want you to think 2.7 every time you see that number e. It looks like I have two variables here, but in fact, I just have one. E is a number. Well, knowing what I know about this, if my base is greater than 1, then I have exponential growth. Looks like that. It goes to this magic point, 0, 1, and this point. Well, I like to know what happens when x is 1. This is, when x is 1, our point is e, which would be very similar to saying 1 about 2.7. Of course, we also have this horizontal asymptote at y equals 0. That's the x-axis. If you happen to be using an Inspire calculator, the e to the x button is going to be right here. So you can put e to the x, and then it allows you to change the x of your exponent. Remember, that's your variable. If I'm asked to use my calculator to evaluate the function, Now, we call this the natural base function, e to the x. That's an important piece of vocabulary to know. This here is known as the natural base function. So y, or f of x, equal e to the x, we call that the natural base function. We want to evaluate this when x is -2. Well, e to the -2, when we put this in our calculator, is going to give us 0.13533353. And I would like you to confirm that on your calculator. If I'm asked to find the value when x is 0.25, then I put this in my calculator, e to the 0.25, which is going to give me 1.2840254. When x is -0.4, I get 0.670320. And finally, when x is 2/3, I get 1.9477340. Now, in my head, I've got this little graph here. And I know that it goes through this magical point 0, 1, and 1, comma, e, which is about 2.7. So I ask, does this make sense? If I'm going x -2, I'm over here. I am expecting a small positive number. Why positive? Because remember, we have this y equals 0 horizontal asymptote. If I'm asked about 0.25, well, if this here is 1, 0.25 is here, I'm expecting a point like that, and it's greater than 1. So that makes sense to me. It should be greater than the y value of 1. -0.4 is somewhere close to this y-axis, and I'm expecting, again, a small positive value that's bigger than this one. How about 2/3? Well, 2/3 is close to 1. I'm, again, expecting a value greater than y is 1 here is my value at this 0, 1 point, and I get almost 2, which makes sense to me. So when you're getting output from your calculator, remember to ask yourself, does this make sense?